Work lifting objects. Let's start by looking at the formula for work done when lifting an object. When lifting an object whose weight may change with height, we compute work by this integral. Work is equal to the integral from y equals a to y equals b of f of y dy. And here, y represents the position of the object. So y is changing because we're lifting this object. Let's jump into an example. A heavy rope, 50 feet long, weighs 2 pounds per foot and hangs over the edge of a building 120 feet high. Part A, how much work is required to pull the rope to the top? Let's go ahead and draw a diagram. Here's a diagram of a 120-foot building and a 50-foot rope hanging off of it. The formula that we're going to use is work is the integral from y equals a to y equals b of f of y dy. Let's start with thinking about our limits of integration, y equals a to y equals b. We can only compute work where the object is. So if we want to think about limits of integration, we're going to need an origin. We're going to need to put the horizontal and vertical axis over this system or overlay it on this system. So what we're going to go ahead and do is decide where we're going to put our x-axis and y-axis. So we have some choices. I'm going to do this in two different ways. I'm going to start by putting the x-axis all the way on the ground level and then the y-axis right here. So this is my origin. Then my limits of integration are going to extend from, well, way up here is y equals 120, and then the bottom of the rope would be at y equals 70. So I'm going to have the integral from y equals 70 to y equals 120. And then what I need to do is find the force at each y value between 70 and 120. And the force is going to be different at each y value. Let's go ahead and pick a random y value here. The force is the weight of whatever's being lifted at that moment. And since the weight depends on how much rope is still hanging, because each foot weighs 2 pounds, so if I start lifting some, the weight is going to decrease over time. So since that weight depends on how much rope is still hanging, the force is going to change with the position. And so here, our force function, or our weight at any given y value, is going to look like 2 pounds per foot times however much is still hanging at this y value. So however much is hanging is going to actually be 120 minus y. So here, I'm going to have to put the expression 120 minus y feet dy. And so let's go ahead and think about how the units of feet are going to cancel here. So we're just going to have a force that is in pounds. So the force is the weight. And then let's just make sure that this formula makes sense. So let's go ahead and say at this random y value, we're looking at y is equal to 80. So if y is equal to 80, then the portion of the rope that we have left hanging is going to be from 80 to 120. So 120 minus 80, that's 40 feet of rope. And so 40 times 2 is 80 pounds. So at that y equals 80, we're going to have 80 pounds of rope. So that's the force at that one y value. So this formula makes sense. So we can go ahead and simplify it a little bit. So we have the integral from 70 to 120. And then I can go ahead and distribute in the 2. So I would have 240 minus 2y dy. So I can go ahead and move forward with integrating this and then substituting in 120 and substituting in 70. And then my units would be in foot-pounds. And I can go ahead and do that. But I actually want to give us another way to set this up. So we chose originally to put our origin on the ground level. So what we could have done instead is we could have gone ahead and put our horizontal axis at the bottom of the rope. So, whoops, we can put our horizontal axis right at the bottom of the rope here. And so now our limits of integration would extend from 0 to 50. So I'd have y equals 0 to y equals 50 as my limits of integration. And then again, there's that generic y value between 0 and 50. So I also could set up that work is equal to the integral from y equals 0 to y equals 50. Still, we're going to have that 2 pounds per feet, but this time the distance traveled at y is going to be 50 minus y. So we're going to have 50 minus y feet dy. And so again, feet are going to cancel. And so this time I'm going to have 2 times 50, which is 100, and then minus 2y. So I'm going to have the integral from 0 to 50 of 100 minus 2y dy. And so these are going to actually give us the exact same answer if we calculate it out, and we will go ahead and finish off this second one. But why would we prefer the second one? Well, because after I take the antiderivative, I'm going to substitute in the limits of integration, and I would much rather substitute in 0 and 50, those are nicer numbers, than 70 and 120. So it turns out we didn't even really need this height of the building here, because it's up to us where we want to put our axes. So that didn't look very horizontal, so I'll move it. That's going to be our choice. And so we should always choose to make our lives a little bit easier, especially if we're going to finish out the problem and perform this integration. So let's do that next. The antiderivative here is going to be 100y minus y squared, and again evaluated from 0 to 50. So we can just go ahead and substitute in the 50, 100 times 50 minus 50 squared, because if I plug in 0 to those, I'm just going to get 0. So what we have is 5,000 minus 2,500, which is 2,500. And the units here are going to be in foot-pounds. So the last thing I want to do here is kind of think about this expression 100 minus 2y graphically. So 100 minus 2y is a linear function. And so what I'm going to go ahead and do is I'm going to graph this force function here. So 100 minus 2y, just a rough sketch. The y-intercept is going to be up here at 100, and the force was in pounds. So we're going to have pounds on the vertical axis. And then we're going to have that slope of -2. And so this value over here is going to be at 50. And this is in feet on the horizontal axis. So this is our force function. And I want us to think about how this makes sense. So initially at 0 feet, the total rope weighs 100 pounds. Yeah, that makes sense because each foot is 2 pounds. So at a y value of 0, if I haven't pulled any rope up yet, the whole rope is going to weigh 100 pounds. And then the weight of the rope is going to drop by 2 pounds every foot. And it's going to go all the way down to eventually 0 pounds once all 50 feet have been lifted. The work done is finding the area underneath this force function between 0 and 50. So we essentially found the area of this triangle here. There is a part B to this question. How much work is required to pull up the second half of the rope, assuming we have already pulled up the first half of the rope? So let's return to our diagram. All right, here's our diagram, and we want to again think about the work required to pull up the second half of the rope, assuming we already pulled up the first half. So our formula is still work is equal to the integral from some y value to another y value of the force function. So we already figured out that the force function is 100 minus 2y dy. So it's really about picking the correct limits of integration here. So half the rope is going to be 25 feet of rope. So the question becomes, are we setting up our integral from y equals 0 to 25 or from y equals 25 to y equals 50? So because we're talking about the second half of the rope, you might be really tempted to put your limits of integration from y equals 0 to y equals 25. But that would actually not be correct. And let's kind of talk about why using this force function right here. So if I've already pulled up the first half of the rope, That part is going to take more work because more rope is hanging down. So all 100 pounds is hanging down initially. So if I pull up the first 25 pounds, the work is, again, it's going to be more. So it's going to be a larger amount because I'm putting in more effort. It's more energy to pull up the whole entire thing, that first 25 feet. The second 25 feet is going to be the easier amount, right? So if only 25 feet is hanging down, that's going to require less energy, less work. So the limits of integration are actually going to be from 25 to 50. So we are actually thinking about the work that is done pulling up this portion right here. Because again, that first half has already been pulled up. So really, this is all that's hanging here at this point. So if I perform this calculation, then I would get the work done pulling up the second half of the rope. But do I have to perform this calculation? No, because what I could actually have done is if 25 feet of rope has already been pulled up, I can move my x-axis, my horizontal axis. So I can go ahead and move that up, and then I can go ahead and integrate from 0 to 25. Y equals 0 to y equals 25. So what I can do is calculate the integral from 0 to 25, but here's where I have to be careful. It's not going to be 100 minus 2y anymore. So it's going to be that 2 pounds per foot, and then how far does a y value here have to move? Well, the distance is 25 minus y dy. So we're going to have the integral from 0 to 25, and then 50 minus 2y dy. And so that should make sense. The total force is 50 pounds initially. The weight is 50 pounds, and then it's decreasing by 2 pounds per foot for each foot y. So this is our new force function. If we've already pulled up half the rope, then we can just go ahead and think about moving our horizontal axis up to make our lives easier for integrating and evaluating. So we can now go ahead and say this is 50y minus y squared evaluated from 0 to 25. If we plug in 25, 50 times 25 minus 25 squared, we have 1,250 minus 625, which ends up being 625 foot-pounds. And so what we did was we calculated this second portion here. So it's the same as this integral up here. It's the same amount, but it was just easier to calculate if we changed our starting index to 0 and if we shifted our horizontal axis. Here we have another example. A 5-pound bucket is lifted from the ground into the air by pulling in 20 feet of rope at a constant speed. The rope weighs 0.08 pounds per foot. How much work was spent lifting the bucket and rope? All right, so let's draw a diagram here. Here we have our 20-foot rope, and it's holding our 5-pound bucket. To compute the work, we're going to need to integrate from some y value to some y value. So we have to put our horizontal and vertical axis somewhere. So I'm going to put my horizontal axis here where the bucket is, and then just my vertical axis right along where the rope is. So we are going to be integrating from y equals 0 to y equals 20. So our limits of integration are going to be y equals 0 to y equals 20. And then I need that force function, which again, the force is going to be the weight, which varies as I lift this from the ground into the air. All right, so we have this 5-pound bucket that's just constantly there throughout the entire problem. So the force, the weight, is always going to include this 5 pounds. So I'm going to start by putting that 5 pounds, that 5-pound weight there, plus, all right, so I'm going to have that 0.08 pounds per foot of rope. So I'm going to have 0.08 pounds per foot, and then times that amount of feet at any given y value. So if I pick a y value here, how many feet of rope are there? Well, it's going to be 20 minus y. So we're going to have that 20 minus y feet, and then dy. So here, again, notice that the units of feet cancel. So I'm going to have 0.08 pounds times 20 minus y. So I'm going to have pounds here, and then plus the 5-pound bucket. So this is all pounds. It all needs to be the same units that I'm going to be integrating. And so let's go ahead and simplify the numerical values. We're going to have the integral from 0 to 20. We're going to have 5 plus, if I distribute, 0.08 times 20 is 1.6. Oops, 1.6. And then minus 0.08 y dy. Or the integral from 0 to 20 of 6.6 minus 0.08 y dy. So if we think about this force function, initially the total force, the total weight is 6.6 pounds. It's the 5-pound bucket and the total weight of the rope. So the total weight of the 20-pound rope, if it's 0.08 pounds per foot, that's 1.6 pounds plus 5. So a total of 6.6 pounds initially. And then we're going to be subtracting 0.08 pounds for each foot we lift up, for each y that we lift up. So this weight function makes sense. It's going to be decreasing over time, and we're going to go ahead and perform this integration. So we're going to have 6.6y minus 0.04 y squared. So add a power, divide by the new power. So 0.08 divided by 2 is 0.04. And we're evaluating this from 0 to 20. Thankfully, plugging in 0 gives us 0. So we'll just plug in 20. And I'm going to skip showing the arithmetic here and just go ahead and let us know that this is 116 foot-pounds. In this example, we have a 20-meter cable, has a mass of 80 kilograms, and is used to lift a 10-kilogram crate. Use gravity equals 9.8 meters per second squared. Find the work done to lift the cable and crate up 20 meters and then up 5 meters. This example is slightly different because we're in the metric system. We're given a mass instead of being given a weight. So we need to multiply by gravity, which is given here, although it technically doesn't have to be. We should be able to recognize that because we're given a mass that we need to multiply by gravity. Let's draw a simple diagram here. So we have a 20-meter cable that's hanging down, and on the bottom of it is a 10-kilogram mass. Now, on this example, we are told that the mass of the entire cable is 80 kilograms, instead of being told that each meter has a certain mass. But we can find out how much each meter weighs if we perform the computation 80 kilograms divided by 20 meters. So we'd get 4 kilograms per meter of rope. So now let's go ahead and start to set up our integral for part A. So if we want to find the work done to lift the cable and crate up 20 meters, let's go ahead and start by saying that the work is equal to the integral from y equals, we're going to go ahead and say y equals 0 to 20. We're going to put our horizontal axis right here at the bottom, and then our vertical axis right along the rope. So we are integrating from y equals 0 all the way to y equals 20. And then I don't want to forget to include gravity here in my force function. So I'm going to put 9.8. And then I'm going to put my mass that I'm going to need to figure out. So the total mass here as a function of y is going to be the mass of the crate at the bottom. So we're going to put 10 kilograms. Plus, well, we had that each Meter is 4 kilograms, so we have 4 kilograms per meter times, well, if I think about just a y value between 0 and 20, that distance traveled is going to be 20 minus y. So we're going to have 20 minus y meters dy. And so the meters are going to cancel. And so I'm just going to end up with kilograms here and then times that gravity so that it represents the weight as a force. And so let's go ahead and do some simplifying. Let's pull out the 9.8 since it's a constant multiple. And then I have the integral from 0 to 20 of 10 plus 80 minus 4y dy. If I distribute the 4 in, 10 plus 80 is 90, so we have 9.8, the integral from 0 to 20 of 90 minus 4y dy. And so we have 9.8, and then the antiderivative is 90y minus 4y squared over 2 is 2y squared, evaluated from 0 to 20. And so let's go ahead and substitute in 20, since substituting in 0 gives us 0. So we'll just get 90 times 20 minus 2 times 20 squared. So let's see, this is 1800 minus, here 20 squared is 400 times 2 is 800. So 1800 minus 800 is 1000. So I have 9.8 times 1000, or 9800. And the units here are either Newton meters or joules. So I'm just going to go ahead and write J for joules. So the work done to lift the cable and the crate up 20 meters is 9,800 joules. Now let's go ahead and take a look at part B. For part B, what's going to change is just the limits of integration. We are going to integrate from y equals 0 to y equals 5. So what we want to do is figure out the work done in lifting the cable up 5 meters. But if I lift the cable up 5 meters, I'm still lifting up all these parts here on top. So the formula for the force is still going to remain the same. So I am just thinking about the work done moving the values that are between 0 and 5. But when I move up 5 meters, I'm moving the entire rope up 5 meters as well. So that's why it's going to be the same formula, and just the limits of integration are going to change. So I kept everything here the same, except I erased that upper limit of integration. So I'm going to replace it with 5 everywhere, which of course is going to change our final answer. And so if we substitute in 5, we're going to get 90 times 5 minus 2 times 5 squared. So we're going to get here 450 and then minus 50, so 400 times 9.8. So 3,920 this time joules to lift up the crate and the rope up 5 meters.